Good afternoon, everyone. Welcome to this research conversation webinar on the issue of relative sea level rise in the Gulf of Guinea. My name is Marie-Noëlle WOILLEZ. I am a research officer at AFD, working on climate change issues in different regions of the world. For today's webinar, we have the pleasure to welcome Assistant Professor Philip MINDERHOUD from the University of Wageningen in the Netherlands, Associate Professor Pietro from University of Padua, Italy, and Professor Kwasi APPEANING ADDO from University of Ghana. So we're together for about 1 hour and a half. So as an introduction, I will briefly present some elements on the global on the issue of global sea level rise and also the context of the study we're going to present. Then I will leave the floor to Philip MINDERHOUD and Pietro Teatini for two presentations of about 20 minutes each on the issues related to measurement of coastal elevation and then on the question of land subsidence. Then we will move to the discussion part with Professor ADDO for another 20 minutes. And finally, questions will be open to the whole audience. Please note that you can ask questions in the chat during the presentation. You've got a button on the at the bottom right of your screen. So feel free to ask a question there. So without any further delay, let's start with a short overview on low-lying coastlines in the face of sea level rise. So, as you probably already know, global sea level is currently rising because of anthropogenic global warming. On the figure on the right, you can see the evolution of the sea level anomaly in millimeter since the beginning of the 20th century, according to tide gauge data in blue and from for about the last 3 decades from satellite radar altimetry in red and green. So the rise is driven by, so the rise is now about 20 centimeters from the beginning of the 20th century. And it's due to 3 factors: thermal expansion of the ocean, which accounts for about 38% of the signal, glaciers melting, which accounts for 41% of the signal, and ice sheet melting, so Greenland and Antarctica, which accounts for about 30% of the signal. The rate of sea level rise is an acceleration. It used to be about 1.9 millimeter per year over 1971-2006, and it has increased to 3.7 millimeter per year in 2006 to on average between 2006 and 2018. These are the last figures from the IPCC report. So 20 centimeter is the global average, and it does not mean 20 centimeters everywhere. Sea level rise is not uniform, as you can see on this figure, which shows you sea surface height change in centimeters from 1992 to 2019. And you can see that in some places in light yellow, the rise has been less than 5 centimeters. And in other regions of the oceans, the rise can be above 10 centimeters over the period. So what about future decades? Well, unfortunately, sea level is committed to rise over future decades, and either it will continue to rise probably for centuries to millennia, whatever the level of future greenhouse gas emissions. But the magnitude of the rise will depend on how much greenhouse gas are going to be emitted globally, and then on the level of future global warming. Here on this figure, you can see the sea level rise projections from the last IPCC report. And you can see that by the end of this century, it ranged between 50 centimeters under a very optimistic climate scenario, where greenhouse gas emissions decrease sharply and rapidly. It's light blue. And in the worst case scenario, where emissions continue to grow rapidly, the rise could reach about 1 meter compared to the beginning of the 20th century. But note that there are actually high uncertainties on worst case scenario, because there are large uncertainties on the future behavior of polar ice sheets, because some processes are either poorly known or difficult to model, and higher values up to 2 meters by the end of the century cannot be excluded in a worst case scenario. And on the longer term, so if we look at the projections for 2300, well, the rise could be of several meters depending on the climate scenario. So this means that worldwide, population who are living on low-lying coastlines are or will be exposed to the risk of flooding and submersion in coming decades or coming centuries. On this figure, it's a recent re-evaluation of the number of people worldwide living on coastlines at less than 2 meters of elevation above present-day sea level. The estimate is globally that 267 million of people live in these low-lying coastlines, with a large part of these people are in Asia, but you can see that also many million of people are in this situation in Africa. And in our study region, so the Gulf of Guinea, so there are between 500,000 to 2 million in Côte d'Ivoire, for instance, and there's also huge hotspots in Nigeria with more than 10 million people exposed. So focusing now on the Gulf of Guinea region, and Professor ADDO will give you more details on the region later, but it's a low-lying and sandy coastal areas with growing big growing coastal megacities, 2 big deltas, so the Volta and Nigeria Delta, and millions of people in the low elevation coastal zones. On this table, there's estimates for the different countries for people living at less than 5 meters of elevation. And you can see that there are more than 40 million in Nigeria, 2 million in Benin, 1.7 million in Cameroon, 1.7 million in Côte d'Ivoire. So in addition, the coastal population is still growing because of demographic change, of internal or international migration, and but because of socioeconomic development. There's a recent study which was published this year from Olusegun Dada and colleagues, was estimated that the main driver of future increase in exposure to sea level rise in the region is actually the fast socioeconomic development in the coastal areas. So sea level is rising. The topography of the coastline of the Gulf of Guinea is very low. There is important socio-economic development in the exposed zone. So there's obviously a need to improve the assessment of present and future exposure to sea level rise in the region to be able to design relevant adaptation strategies and to avoid any locked-in trajectory. But assessing exposure to sea level rise is actually not so simple. Several things need to be considered. First, we need good quality elevation data, and this is not so simple, as Philip is going to show you. And we also need to take into account potential vertical land movement, especially if the land is going downward. It's called subsidence. It will increase what we call the relative sea level rise, and this will be the topic addressed by Pietro. So in this context, AFD has financed last year a scoping study to assess the vulnerability of the Gulf of Guinea coastline to relative sea level rise. This study was performed by different researchers from University of Padua, of Wageningen, of Urbino, University of Ghana, and University of Lagos. And this study had 4 main objectives. First, provide a new coastal elevation assessment of the Gulf of Guinea region to assess exposure to sea level rise. 2, perform a literature study on coastal vulnerability. 3, to focus on 2 local case study at the country level. So the focus country were Ghana and Nigeria. And 4, to identify the main knowledge gaps and critical geographical area. So the results have been published this year in 3 AFD research papers, which are all available on the AFD website. You can have a look at these papers for more details. But some of the results are going to be presented today by our colleagues. And so now, well, I leave the floor to Philip, who will introduce the issue of measurement of coastal elevation. Philippe, the floor is yours.
Thanks a lot, Marie-Noëlle. And also from my side, welcome everyone to this webinar. It's a pleasure to have you here. My name is Philip MINDERHOUD. I am from the University of Wageningen and University of Padua, and I'm an assistant professor there. And in the next 15 minutes, I'll take you on the journey to coastal elevation, and not as straightforward as often assumed. So let's unravel that. So first start in the coastal zone and the changes and impacts that are happening around the world. So in italic, we see the changes that happen in these places. Of course, there's a change in climate, but there's also local changes. This can be the expansion of urban centers, population growth, but also change in land use, extraction of natural resources. This could be groundwater or sand, or upstream mining, changing water and sediments to these coastal zones. And as a result, in these coastal areas, there are impacts. So and they're visible in bold. So for example, an increase in the amount of flooding, an increase of salinization, coastal flooding, coastal erosion. And then if we move to the right-hand side of the figure, as Marie-Noëlle already talked about, and presumably you all know, we have global sea level rise, but also the level of the land is not static. So many of the coastal zones around the world are experiencing land subsidence. And the combination of sea level rise and land subsidence is what is indicated by the yellow arrow. And this is what we call relative sea level rise, or in other words, the experienced sea level rise when you're standing at the coastline and you experience both the movement of the seawater and the movement of the land. So actually all these processes that you can see in this diagram, they are linked in one way or another to the elevation of the land. And small elevation changes in coastal zones can have very large consequences. So let's see at what point are we actually here in the year 2023. So for example, if we go to this place, I believe it's in Senegal, and we would stand at the place of the arrow, and we would want to know our position, then actually all of us can just take out our smartphones and we use our desired app, for example, Google Maps, and within seconds we get the position where we're standing on a horizontal plane with an accuracy of several meters. And generally we are very happy with that because we can navigate, we know where we are. So the accuracy of a several meter difference that we get in that information is not a problem for us. We can really work with that. Then at the same time, if we would want to know the elevation of this point, we could try to use a similar app and also get an estimate of the elevation. And again, this estimate of elevation has an uncertainty of several meters. While standing at the coastline and looking at the water level, that actually creates a lot of issues, because an uncertainty of several meters, when we are talking about sea level rise, which is in the order of millimeters to centimeters per year, that is really a large error. And actually that is one of the main points what is making, let's say, vertical information not that straightforward. Why is knowing coastal elevation so difficult? In some countries, there is high resolution in the vertical reference elevation data available. This can be, for example, LiDAR. So this is measured by laser from airplanes. It can be from GNSS stations. These are positioning points using satellites to high accuracy positions. But often this data in many countries is either not available in the first place, or it is not available in the public domain. And this leaves then actually the only source of data, which is the globally available elevation data. So we live in an age that we have satellites orbiting the Earth, measuring a lot of things, and one of it is actually the Earth's elevation. And these data sets are freely available, for example, through NASA or ESA, and this is also what you would get as data underlying the smartphone application if you want to know the elevation of a certain spot. However, there's a few things that you have to keep in mind when you have these data sets. First of all, they have quite high, relatively, so to say, vertical error, so up to several meters. And of course, if you are in a mountainous area, several meters in the vertical direction is actually not a big issue relatively to what you want to know. But if you are standing at the coastline, this several meters, they cause issues. A second issue, which is often problematic, is that the data, the elevation data, is referred to a general common datum, which can be a global datum, for example, a geoid or an ellipsoid, but they are not necessarily one-on-one linked to what is actually the global elevation, the global level, the local level of your sea level. So in order to do so, you need to convert from this global reference frame to a local reference frame connected to sea level. And also that can create errors and uncertainties, offsets up to several meters. So all in all, this is quite problematic in the view of sea level change, which is in the order of millimeters per year. And as a result, there's quite a high level of uncertainty available in a lot of the impacts assessments that we see in many countries around the world, used by either governments, NGOs, development banks, but also in science. And this creates a lot of issues, even until today. I'll show you two examples before we move to the Engulf data. So the first example is from the Mekong Delta in Vietnam. And here you see on the left side, panel A, elevation data. This is the SRTM elevation model of NASA, which is it's one of the widely used data for assessments. And on panel B and C, you see derivatives that show the area of impact by certain meters of sea level rise. Well, in these maps, they have been used until quite recently in a lot of policy documents and development documents, such as the Asian Development Bank River, Mekong River Commission, and they're even used to guide investments, for example, to understand which of the provinces in this delta are most vulnerable to sea level rise. Actually, when we started to dig into this delta and we managed to get local high accuracy data, we could create a local elevation model. And this is what is referred to here as the topo DEM. And what is really striking, if you compare that to the earlier available satellite-derived DEMs, is that the average elevation of this delta is more than 1.5 meters lower than what was assumed based on the satellite data before. And in this case, the biggest offset, the biggest change was created because of the difference between local sea level and the global geoid to which the elevation was, the satellite elevation was referenced. And this has, as you can imagine, huge implications, because all of a sudden, this area where a lot of people are living and a lot of economic and agricultural activity is taking place was more than a century sea level rise lower than it was before. So it completely changed all the future impact assessments of a relative sea level rise. And actually, it also learned us that this may be the case in other places in the world. Well, a second study that came out this year, actually, by Katarina Seger, and she did a similar study on the Irrawaddy Delta in Myanmar, comparing a lot of the available elevation models, older ones, but also the most recent ones that are really try to reduce a lot of the errors. And what you can see in this figure is that there is an enormous spread on the area that is impacted by relative sea level rise based on the elevation data that you use. So this really shows that it really matters a lot when you which DEM you choose and which DEM you choose to move forward with, because it completely dominates your assessment. A conclusion of this study was that what was called the FAP DEM and coastal DEM version 2.1, which are both last generations updated global elevation models, they showed the best agreement with a local elevation model in this delta. So this is one of the things that we learned from here, and we also took to heart in our study. So let's move to our study area, the Gulf of Guinea. And what we did in the scoping study is we wanted to understand what are actually the low-lying elevated zones of this Gulf line that could be under influence of relative sea level rise. So we compared 5 different elevation models. So we selected the most promising ones based on other studies and included also an old legacy one, the SRTM DEM, for comparison. So these are the most advanced ones that you can get. We have corrected them to local sea surface height using Aviso data, which is shown on the right top side. And what you can see in the transects that are showed here, so these are transects running from the coastline inward, land inward, is that still along these, let's say, respectable DEMs, there's a lot of difference in order of several meters between the different elevation models. So also that shows you that picking a single elevation model means you are, in that sense, tied and restricted to errors and uncertainties of that single elevation model. To illustrate it a bit further, we have here the first 3 panels. They show a part of the city of Accra in Ghana. And as you can see, the first elevation model shows almost no area below projected sea level, while the FAP DEM and the coastal DEM, the second and the third panel, they show a much larger area affected by potential sea level rise. And we see the same thing on the panels below for the Niger Delta in Nigeria, that there's an increased amount of area affected according to several DEMs. What we decided to do in the study is not to be reliant on a single elevation model. We chose to work with a DEM ensemble. And in our case, we selected both the FAP DEM and the coastal DEM 2.1, as you can see in the last panels on the right side here. And that's what got also the best results in our validation of the study, which we had just a few, but we had some local elevation points to come up with and to validate them. And this is what came out of the analysis for the entire coastline. And this is led by our colleague Leon Hauser and reported in the research paper on this. And what you can see here, we see the entire stretch of the study area, and it shows in green all the areas elevated lower than 2 meters above current local sea level in one of the 2 DEMs. If it's light green, it only flagged in one DEM. If it's dark green, it is flagged in both DEMs. So our certainty that it is actually elevated below this 2 meter threshold goes up when you see the dark green. Then in addition, we also put another layer of analysis on top of it, which is a land use layer. And we checked to see if some of the low-lying areas coincided with either cropland, agriculture area, or a build-up area, so to say urban areas. So whenever you see a color arriving, for example, the pink or the red colors, those are low elevated areas where we also identified the high-risk land use. So there are assets that can be lost when we talk about relative sea level rise. And as you can see, we made some zoom-ins on certain spots that have large areas of low-lying land. For example, around the city of Abidjan, there's a lot of low-lying area. The Volta Delta in Ghana, Cotonou and the area north of Cotonou, the area around the city of Lagos, and of course the Niger Delta itself also has a low elevation. So this shows us basically the hotspots, so to say, for the Gulf of Guinea with respect to relative sea level rise. And to conclude this part on elevation, some take-home messages. So the satellite-based DEMs, they provide a good first indication of low-lying areas. Of course, we want to check, and they need to be checked with localized data. The estimates between the DEMs, they vary considerably. So that means, and that's the reason we use multiple DEMs, and it's a word of caution when you use such elevation data with sea level rise impact assessments to really understand what you are using with. We actually are almost finished with a policy brief on this matter, which conveys the information in more, let's say, readily to use steps, how to use elevation data in the coastal zone. So if you're interested in that, keep a lookout for it. It will be shared on the website for sure. But then knowing land elevation at a single point in time, that is of course not enough, because these coastlines, they're first of all highly dynamic, they change, and secondly, the land level is not stable, as we can have land subsidence and relative sea level rise over time. And with that, I'd like to give the floor to Pietro Teatini to talk about these issues. Thank you.
Thank you, Philip. So good morning, good afternoon to everyone, and I'm happy to have a lot of people here in this webinar. So what I will introduce you is this process that affects several countries all over the world, that it is land subsidence. So for land subsidence, we mean the loss of land elevation. And this loss of land elevation is generally or mainly caused by human activities. Here, just a couple of pictures or photos taken in different countries, Indonesia, Netherlands, and Arizona, where we can clearly see which is the effect of this lowering of the land surface with respect to the sea, with respect to a channel, or also in arid inland zone, where we can see that huge cracks can occur simply due to the fact that we develop too much the groundwater resources that we have at depth. So what is land subsidence? Just a short introduction. I think that most of you already know, but just to make a short introduction, why the land surface moved downward. This is strictly or generally related to the fact that people need water, need fresh water, need water that it is not polluted for their usual activities. And this is mainly located in the subsurface, generally called aquifers. Aquifers are, they contain an enormous amount of good quality fresh water, and therefore much more than on the river, for example, or lakes that are much more exposed to contamination. So what happens when we remove some groundwater through a wells, for example, from an aquifer system that it is located at a certain depth below the land surface? Generally, it happens that we decrease the pressure of the water. The water is located in the pore space between the grains that compose our aquifer system. And this pressure is fundamental. The pressure of the water into the pore system is fundamental to keep part of what it is called the geostatic load. So really, soil has a weight, and the weight of the soil act or try to compact the soils that are located at a larger depth. And this load, this weight, is partially supported by the pressure of the water in the pore system itself, and part by what it is called the effective stress, so the stress that each single grain couples exchange within the soil subsurface. So as soon as we take out groundwater, so from using, for example, a well, we decrease, therefore, the pore pressure, and we can measure it very easily through a piezometer. So we observe a lowering of the piezometric head. This caused that as the pressure decreases, but the weight of the soil column remain exactly the same, this the component or the portion of the geostatic load that is maintained by the vertical effective stress, so by this grain-to-grain contact, has to increase. This gives us, let's say, this physical behavior is described very well by a very simple equation that, let's say, it is quite known, at least for engineers or geologists, that it is called the Terzaghi principle. Geostatic load is equal to the effective stress plus the pressure of the pore, of the water that it is located in the pores. As soon as we have that the effective stress increase, so the stress that the grains experience increase, this causes a compaction of the aquifer system, the layer that it is located at depth from which we remove the groundwater. If a layer that it is located, for example, at a depth of 100 meters, reducing thickness because it's compact, of course, the land surface that it is located above that compact unit move downward. And this is what we call it land subsidence. Just to explain a bit, we can make a simple comparison, and this is these two, let's say, funny photos that you can find on the bottom of this slide, just to explain the physical process. Okay, if we have a bowl, and this bowl is simply filled by air, so the air is a fluid. The bowl filled by air is able to keep the huge weight of this guy that it is seated above the bowl. It's exactly the same. This we can assume that the bowl is a big pores. The pores in this case is filled by air, but air is a fluid, more or less similar to water. So the pressure of the air into the bowl is able to keep the guy sit on the ball itself. But let's suppose now that for some reason we have that the valve of the ball fails, so we decrease the pressure of the fluid into these big pores. What happens? It happens that the pores collapse and the guy moves downward. So this is really similar to what happens in nature in an aquifer system as soon as we start removing groundwater, and therefore we decrease the pressure of the water that it is located into the pore networks. So which are the main factors then that contribute to have large subsidence or more subsidence? There are several factors, but I think we can sum up into 3 or 4 key parameters. One that are listed in this slide and shown in this figure. First of all, what it is important to know is the depth, the burial depth of the aquifer from which we remove our groundwater. Second one is the compressibility of this soil. We have soil, everyone knows, for example, that clay-lay soil are much more compressible than sandy soil. So if we cause some pressure change in a clay unit, we have to expect more subsidence than when we remove groundwater from a sandy unit. So compressibility is fundamental. Of course, it is very important also how much pore pressure decline we made in our aquifer system. And lastly is the thickness. The thicker is the layer, the larger is the subsidence that we can cause as soon as we decrease the pore pressure into that layers. Subsidence, we say that subsidence is affecting an unbelievable number of countries all over the world. In these slides, I just reported few very well-known case studies of land subsidence that are affecting coastal zone. And let's say, so we have area in the US, for example, New Orleans, we have area in Northern Africa, the Nile Delta. we have several areas in Asia. I think that nowadays we can say that Asia is probably the continent when land subsidence is much more affecting the coastal zone. The most important or the most evident and clear example nowadays is Jakarta, the capital of Indonesia, that has subsided at about 260 millimeters per year. This means that there are some portion of the city that every 4 years they lost 1 meter with respect to the nearby sea. So an enormous amount of land subsidence. Fortunately, this number does not happen all over the world. But for this city, let's say, they are really unlucky, in an unlucky situation. What we know about now the Gulf of Guinea about land subsidence. There is a group funded by UNESCO that it is called Land Subsidence International Initiative, managed by UNESCO, that a few years ago make a studies published in Science, where we try together to map the so-called global threat of land subsidence. So where there is the largest susceptibility to land subsidence, where there is the largest risk of land subsidence, and where this can occur. There are several regions, and the map on the top, you can see the red colors means the area where this land subsidence is potentially the largest value. But when we move to the Gulf of Guinea, and this is what we have in the figure on the bottom left, we can see that we have some color, but we also have these hatched lines, gray lines, that contract this area. What this means? It means substantially that for this region, there are very few information. At the end, we are not able to perform any evaluation, any quantitative evaluation for this area, because the available information there are too few. And therefore, one of the main aim of Engulf is really to try to remove this gap and to understand if this part of the coastal area of the African continent are potentially subject to land subsidence now and also in the future decades. Well, if we go to the field, what we can see, these are some photos taken by Femi Ikumeranus, that it is a postdoc that it is working in our project, and that he's a Nigerian researcher. He lived there and he moved through the city. And when he moved through the city and took some picture, you can see that there are some evidences of buildings that are damaged in structure. There are buildings that seems permanently flooded or temporarily significantly flooded when there is some strong rainfall events. So this signal seems to suggest that potentially land subsidence is already occurring in Lagos. Lagos is really not a possible hotspot of significant land subsidence due to the fact that the city is huge. There are more than 20 million people that live there, and the majority of them do not have the possibility to have a direct access to water. So they really rely on their own private small wells from which they take some water, the water that they need to live in the city itself. So we also made some analysis of which kind of information are nowadays available for Lagos. We start from this city because it is, let's say, the main hotspot of possible land subsidence along the coast of Guinea. And we are able to find some results that has been obtained in terms of mapping land subsidence using a methodology that it is called interferometric synthetic aperture radar, INSAR. It's a powerful methodology developed since 20 years ago, that it is nowadays used really in several countries all over the world. And this methodology gives us the possibility to measure the displacement of the land surface, and this measurement, however, has we have to say that this measurement has some problem, in the sense that, as you can see, for example, from these images, these 4 images are maps of land subsidence published over the last 5-6 years by different authors, and they do not show the same displacement rate. They show different value of land subsidence. And so this is really, in some way, contrasting outcomes that it's make, let's say, the use of this data quite challenging. Why this happens? It is well known that this INSAR data are data that provide land displacement relative to a certain position. So they are not absolute measurement of the displacement, but these are relative measurement of the various point, the various radar target with respect to a certain point that the author have selected as reference point. So they are not absolute measurement. So how we can move? We need absolute measurement, of course, to move from this map to something that it is then useful in understanding the potentiality of the possibility of sea level rise and flooding related to relative sea level rise. The only way to do this is to, let's say, use some ground truth, and especially to use some permanent GNSS data. But in this country, and I would say also we make some detailed search, along the whole country of the Gulf of Guinea, there are no permanent GNSS stations. So this is really a huge gap that must be solved as soon as possible. So we also, let's say, also try to understand which the map, the displacement that I showed you before, which are the reasons of those displacement, which are the causes of the observed displacement. We have at this case to understand which are the processes of causing land subsidence or causing those movements that we observe from the satellites. To do this, we must know some fundamental data about the hydrogeological setting of Lagos, for example, if we focus on the city of Lagos. These are fundamental, okay, fundamental to understanding which are the reasons of the observed land subsidence. And it is even more fundamental if we want to make some prediction about the possible amount of land subsidence in Lagos in the next decades. So which are the data that we need to make this job, to make this research? We need some data related to the hydrogeological structure of the subsurface, data related to the hydrogeomechanical properties of those soils. We need data about the groundwater withdrawal, how much the aquifer has been exploited right now, and which is, let's say, the future trend, how much water probably will be removed from those aquifers in the next decades, taking into account that, as Marie-Noëlle showed, the population is predicted to increase even more than the 20 million that live there now. And of course, we also need some measurement related to the evolution of the piezometric head. To try to have this data, we have contacted and visited the main institution that manage this kind of data, this kind of processes in Lagos and in Nigeria. So we have tried to involve into this into Engulf studies some of these institutions, for example, the Lagos State Ministry of Environment and Water Resources, the 2 universities of Lagos, and then the Nigerian Hydrological Survey, the Nigeria Geological Survey, some Lagos State Bureau of Statistics, and the Lagos State Water Corporation, but also some private companies that deals with water management and construction engineering there. We have also in contact with UNESCO and the World Bank that have some headquarters in Nigeria. Unfortunately, let's say all these institutions, when we went there and we try to have this content, they are very, let's say, they respond very positively. All of them are interested in collaboration. They say that all are available to provide some interesting data and in order to build up a serious evaluation, a reliable evaluation. But we have to say that unfortunately, up to now, no data really has been supplied. Let's say the only institution that really has, we have let's say, really a feedback in terms of water availability until now is the Lagos State Water Corporation. So we hope that in the next futures, also the other institution will start to collaborate effectively. Then to conclude, okay, so which is the take-home message from my part? For sure, we have to say that land subsidence is expected to affect also the low-lying coastal area of the Gulf of Guinea. We don't know how much, and this is a key point to be addressed, and that Engulf want to address. Looking at the few data that we were able to achieve until now, we can see that for sure Lagos could be a main hotspot for our investigation. Unfortunately, we have to say that the results that we are able to collect until now are not consistent. So we really need ground truth data. So we really need the possibility to install as soon as possible permanent GNSS station in those areas, and also to maintain them in a good functioning. We also need hydrogeological data, and we have started working with the local authorities and institutions. We hope that they will become more proactive than what we have until now in the near future. Why this is extremely important? Because we have to keep in mind that land subsidence is irreversible. It means that when the land surface moves downward because the pore pressure into the aquifer decline, even though we stop removing groundwater, pumping groundwater, and therefore the pore pressure returns back to the original value, the land surface will not rebound. It will remain at the minimum level. So land subsidence is irreversible. One, we have a loss of elevation, that loss of elevation remains permanently. So this means that it is extremely important to prevent land subsidence. Prevention in this case is much more preferable than mitigation and or adaptation strategies. Thank you. And with this now, I pass to Professor ADDO for his discussion presentation. Thank you.
Thank you very much. And I will look at or kickstart the discussion by looking at the Gulf of Guinea coasts. So I will give a brief background about some of the threats within the Gulf of Guinea coast and how these threats are influencing the issues with regards to subsidence. So that will be a kickoff to the discussions, which I think it's very relevant moving forward. So the West Africa coastal zone is defined as the 25 kilometer from the shoreline, and it has a total of about 1,000 kilometers in terms of length. And this area is very important because it hosts major cities in West Africa, and almost all the very important industries are located within the coastal zone. And we can also talk about oil activity, oil exploration, and oil production within the coastal. So it makes the coastal zone in West Africa very, very important. Again, it is a highly populated area. It's been reported that it is home to about 31% of the region's population. And this is growing at a rate of 4% annually. So it indicates that very soon we are going to have huge population within the coastal area in West Africa. Currently, about 22.6% of Nigeria population live along the coastal zone, while in Senegal, a significant percentage, around 60% of the population is reported to live within the coastal area. In Ghana, the coastal area is relatively smaller, but we have about 25% of our population that live within the coastal area. The West Africa coastal zone has 5 main profiles from the north to the south, and this includes a relatively straight shoreline orientation in the north. And in addition to the straight shoreline orientation, we also have estuaries there. We have mangrove coastlines around the middle part or the central section. Again, we have rocky headlands that are interspaced with beaches. And with the southern side, we have vast coastal areas in terms of beaches. And then we also have deltas such as the Volta Delta in the southern area. The area is highly dynamic, and about 50% of the coastal zone within West Africa is reported not to be habited. And development of built-up areas and urban areas are closer to the shoreline. It's been reported from a study that the rate at which development and settlement are moving closer to the shoreline is higher than the rate at which the shoreline is moving to the inland. And again, increasing production systems that are closer to the sea area are, emerging. We can talk about emerging salt production. There's a big salt production activity going on in Ghana here. And they are increasing, the industries are increasing. And I must say that there are diversity of systems in the coastal area within the West African coast. So what are some of the issues that are threatening the West Africa coastal area? One is population growth and rapid urbanization. This has intensified pressure on coastal resources and infrastructure. I must say that informal settlements in high-risk areas lack proper infrastructure, making them particularly vulnerable to disasters. We can also mention pollution and improper waste management activity that impact the ecosystem. There is also increased demand for land and resources, which leads to unchecked urban expansion, often without proper planning. We can also talk about encroachment in the coastal zone, which weakens the natural buffers like mangroves and exposing urban areas to greater risk from storms and erosion. And we can also talk about the high-level deforestation of mangroves through overharvesting, which has the tendency to weaken coastal resilience, as their removal has left several coastal areas defenseless and vulnerable to erosion and flooding. Generally, the coastal developments, such as offshore activities like oil and gas operation, we can also mention ports and harbor expansion along the West Africa coast, have contributed to coastal challenges in several ways. And these are some of the activities that are really threatening the coastal area. We can also mention nearshore development and say that this development has affected sediment dynamics, resulting in reduced sediment budget and increased erosion in the more vulnerable areas. The absence of land use planning significantly worsens the impact of relative sea level rise and undermine coastal resilience. And we can also mention that the removal of natural coastal defenses like mangroves has increased and amplified vulnerability to coastal erosion and then to storm surge. So these are some of the activities that we can talk about. We can also mention hydroelectric dams, which has played significant role in exacerbating coastal relative sea level rise and compromising coastal resilience. In our quest to develop and generating power through the process of damming, we trap the sediment. And these trapped sediment result in reduced sediment supply to the coastal system, which eventually result in increased erosion. We can also talk about threats posed by coastal defense structures, and these defense structures affect sediment transport. And these defense structures, like groins, in our quest to manage erosion, we normally use a knee-jerk approach. And this knee-jerk approach, where groins are planted all over the coastal areas, trying to trap sediment and build beaches where erosions are rampant, we tend to affect the sediment system. And once the sediment systems are affected, erosion is transferred from one location to the other. And all these result in increasing threats within the coastal area. So the coastal areas are highly unstable, and this instability is as a result of the sediment imbalance with the system. And this sediment imbalance, or the sediment situation in the system, is critical and is important for the growth of the beach and the dune systems within the coastal zone. A situation whereby you have more sediment coming into the system than sediment being taken away from the system, then you have a stable, environment. A situation whereby you have less sediment coming to the system compared to sediment being taken away from the system, then you have an unstable system, and that unstable system can obviously result in increased erosion. But a situation whereby you have more sediment coming into the system being equal to sediment being taken away from the system, then we can say that the system is stable. And once the system is stable, then you have a healthy coastal environment. That is what is happening, where dams are being constructed, and these dams are resulting in imbalance in the sediment system. And this imbalance in the sediment system can also explain some of the activities with regards to subsidence that we are experiencing in portions of the coastal area, especially in Ghana within the eastern coast. So this shows some of the impact of erosion. Unfortunately, several studies in the region have mostly attributed drivers of coastal hazards to climate change without assessing the potential influence of coastal subsidence. So these are some of the impacts, and we most often we attribute changes within the coastal area to climate change without looking at the impact that subsidence is playing. And it's easier, attributing to climate change. But large subsidence is being synonymous to sea level rise when it comes to their general impacts. In most cases, locally amplifies the sea level rise and its devastating effect, therefore accentuating the need for subsidence to be incorporated in coastal studies. And as Pietro rightly indicated, there is the need to understand the subsidence regime within the coastal area in the Gulf of Guinea, because attributing everything to climate change may not necessarily be the right answer to the challenges. So in our attempt to understand the complexity underpinning the recurrence of coastal hazards, an Engulf scoping review on available literature for Ghana generally indicated a limitation in the number of studies carried out, especially in the case of subsidence, which is comparatively understudied. Unlike sea level rise and vulnerability, little is known about the full spatial variability of subsidence, its processes, the drivers, rate, and impact, especially within an African context. And some of the knowledge gaps identified is the absence of a ground validated subsidence study, no long-term and continuous monitoring regime, and non-identification of potential local subsidence drivers, huge deficit in available data for numerical modeling of coastal subsidence. So the Ghana coastal area is, as I mentioned, it's a small area, just about 7% of our landed area in Ghana, but this small area is occupied by about 25% of the population. And industries in Ghana are located within these, small enclave, and therefore pressure on the coastal systems and the coastal zone is extremely high. And because of the high pressure in the coastal system, subsidence being looked at in the western area should be extended to all the other portions of our coastal area. So what take-home message am I leaving you with? There is the need to adopt a regional approach in looking at subsidence, just like the WACA project is looking at coastal erosion management. The WACA project is looking at coastal erosion management within the West Africa region. I think we need to upscale the subsidence studies like the WACA and make it a regional study so that we can understand the subsidence regime within the coastal area in West Africa. The need to set up a robust monitoring scheme. We need to have a robust monitoring scheme, continuous GNS station and elevation benchmarks, mapping of aquifers and routine hydrographical data collection. There is also the need for employment of advanced INSA measurements, alternative sources of fresh water instead of groundwater over abstraction, which increases the rate of subsidence. Switching to more renewable, environmental friendly energy sources. We believe that we have huge potential when it comes to solar. We have huge potential when it comes to wave and tidal energy harvest, instead of over-reliance on hydroelectricity, which is as a result of damming the major rivers that supply sediment to the ocean systems. And once these dams are constructed, as I mentioned, they affect the sediment flow into the system. And lastly, reducing catchment area modification and upstream river abstraction. So this is by way of introducing the discussion, and I want to thank you very much for your kind attention.
Thank you very much, professors. Thank you, Philip and Pietro. Before, Sylvie, can you share the slides again, please? Oh, sorry, I needed the slides back. Thank you. Just before we move to the discussion and open the question to the rest of the audience, I would like to say a few words on the Engulf research program, which was mentioned during the presentation. So the Engulf program is a program who started last year and who's it's a 2 years program, which is running until the end of 2024, approximately. So the acronym is for Coastal Land Subsidence in the Gulf of Guinea. And the aim is to assess relative sea level rise and land subsidence of coastal megacities and river deltas along the Gulf of Guinea. You can find more information on the AFD website. You've got the website address just on the slides. So what are the topics tackled by this program and the expected results? So there will be, so there are different work packages, and the topics tackled are the following. First, to provide new subsidence assessment, so for current subsidence rates with inter-analysis for the whole coast from Côte d'Ivoire to Cameroon. Second, to provide improved coastal elevation assessment and new relative sea level rise projections for the area, and to perform in-depth subsidence analysis for some hotspots, so either delta or megacities. So currently we're focusing on the Volta Delta and the Lagos area. So for these hotspots, so such as Lagos and the Volta Delta, the objective is to try to collect, as Pietro mentioned, some subsurface data, hydrogeology, geomechanics, etc., to be able to set up numerical models, and then to provide, to perform some simulation to provide process-based subsidence projections according to different scenarios. But of course, this relies a lot on available data, and we really depend on that. We also wish to build a regional community of interest on this issue of coastal land subsidence in West Africa. And we will organize next year a webinar series on different topics related to this issue. We also plan to organize we will organize in Ghana the first West African coastal area regional workshop on coastal land subsidence, probably in fall, to be confirmed soon. And of course, so the results will be published through a research paper, and we also plan to have some more policy documents like policy brief or short summaries to perform some outreach, to provide some outreach documents and to accompany outreach events. So more results, more information, and more results to come, hopefully next year. So now let's move on. I would like to thank, of course, our three speakers. Thank you all for your attention, and open the question to the whole audience. So please feel free to ask question in the chat, or raise. I'm not sure if you can raise your hand actually, but you can ask your questions in the chat. And we've got about half an hour to take as many questions as you wish. Thank you. So maybe while people are typing question, there was one already on the issue for you, Philip, on the issue of elevation models. You mentioned the different artifacts that can be there, and there was a question on whether the results you have shown were based on a surface model or terrain model. Maybe you can give a few more information on that.
Yes, I can. First of all, thank you very much, Taco Bruce, for this question. Of course, when the raw data is measured by satellite, it contains, let's say, all the reflectors of the radar signal. So in that sense, it picks up any object at your surface. It could be buildings, could be vegetation. If you want to convert it to a data set that is useful for the projection of sea level rise or flooding, you actually are not interested in the elevation or height of a building, but of the Earth's surface. So to say, in a city, you want to know the street level, or you want to know the level of the soil in an agricultural area. In order to do so, the more recent elevation models, they try to remove these, let's say, biases created by buildings or vegetation. And the DEMs that we chose in the end for this ensemble, so first of all, the coastal DEM 2.0, it does remove, or at least tries to remove, the tree height. So vegetation is corrected. It does not exclude the height of buildings. So that is still in that elevation model present. The FAP DEM actually tries to remove both. So it removes both vegetation and buildings from the DEM. And the way that they do it is through its different approaches. So the FAP DEM uses a random forest approach, which is a machine learning approach. Coastal DEM uses a neural network approach. Basically, these are machine learning, deep learning approaches that try to merge different data sets and then, based on that, remove these biases from it. So your direct last question, yes. So let's say the combined ensemble contains, let's say, both of them contains removal of vegetation. One of them also removes the buildings. And currently, those are, to our knowledge, the best two elevation models, most advanced elevation models globally available, and that's why we use them in this at this stage. But we also have some more ideas to improve them ourselves further on, and that's work in progress.
Thank you very much, Philip. We have a question, maybe rather for Professor ADDO. about if there is currently already ambitious projects to fight impacts of relative sea level rise in the region, either adaptation or prevention. And I think it's indeed a very good question.
Yeah, thank you. Thank you very much for the question. Yeah, there are projects that are going on to try and address the impact of sea level rise. Presently, we are having challenges with flooding in the low-lying areas, and we're also having challenges with increased coastal erosion. And of course, areas where we have high level vulnerability with a little bit of storm and storm surge, you tend to have flooding being exacerbated in those areas. So governments in the Gulf of Guinea are now using more of a mitigation approach in trying to manage the impact of sea level rise. And in areas where the challenges are very high, especially in Ghana, we have groins and revetment being constructed. And these, I am not a fan of hard engineering approach in managing some of these coastal hazards, because you don't manage the problem. You rather transfer the problem from one location to the other. In addition to that, there are also the approach of using ecosystem-based, measures in trying to manage some of these challenges that are being driven by sea level rise. So areas where we have depleted mangrove forest, there are efforts to enhance regrowing and then protecting the remaining mangroves in the areas. So there are efforts to look at how ecosystem-based approach could be adopted in managing some of the issues and challenges associated with sea level rise. So yes, there are projects that are going on. I can talk about a lot of projects in Ghana that are looking at some of these things, and I'm involved in some of these projects. Thank you.
Thank you very much. There are also three questions about the issue of I would say around data acquisition issue. One of if there is a potential for using drones to acquire some data, and also what are the main barriers for further implementation of GNSS stations to get some more data. So maybe this one is for Pietro.
Yeah, thank you. Thank you for the questions. So what about drones? I would say that, let's say, this area, at least the focus of Engulf is to work at a huge, let's say, at the regional coastal scale. Therefore, I think that at least for this stage, drones cannot really be implemented. If you go to Lagos and see how big this cities, for example, is, it takes, I would say, 1 day to move from one side to the other side of the city. It is more than 100 kilometers long. So working with drones, I think that at this scale is not possible. So it could be, they could provide some useful outcome, but possibly in a second stage, in a second project, when we will focus on a smaller scale, smaller hotspot than an entire delta or an entire cities as Lagos. About the GNSS, for sure, one main problem is an economic problem. I think this is for sure the first point. GNSS station, a normal GNSS station, the cost is on the order of 20,000–30,000 euros. So up to now, I think that, let's say, at least for this Engulf study, there is no budget related to this. But we hope that with the outcome of our project, some other funding agency or private agency, or also the local government there, will understand how important this GNSS station are, not only in Lagos, not only in Nigeria, but for sure in Ghana and also in the other countries facing the Gulf. We have to say that we hope that in a quite short time, within the LASI, this group initiative that work within UNESCO, we have a friend, one of the members is from Taiwan. This guy he has a small company really developing technical equipment at the very high level, and they are trying to develop some cheap GNSS station. So we hope that, let's say, within the Engulf project, we will also have the possibility at least to put in place a few of them and trying to use it. So this is some work in progress, but for sure, this is, let's say, the main stage now presently.
Thank you very much. There was a question also, I think, for Professor ADDO about, are there any plans for relocation due to sea level rise in the region?
Yeah, thank you very much for the question. I think relocation is a major issue and very topical when it is raised. Although is one of the management tools when it comes to managing the impact of sea level rise, flooding, and coastal erosion. It's been a major issue because Ghana, we've raised and talked about it, the possibility of relocating people in vulnerable areas. But the challenge has always been the cultural dimension. You know, people are not too comfortable moving from an area that they've been so used to. Some will tell you we have our ancestors buried here. I remember we had discussion with one vulnerable community, and the members of the community were saying, I have my grandfather buried here. How can I leave the bones of my grandfather here and then move out? So it's a big issue. And then again, in most West African countries, we have chiefs who are community heads and community leaders, and we give a lot of reference to our chiefs. Now, several communities have their own chiefs. So if you relocate a community to another community, is the chief going to still be the chief in that community? So these cultural dimensions and social dimensions are making it very difficult for people to accept the option of relocation. But I think last 3 days, there was major flooding activity in one of our vulnerable coastal areas. And the issue came up again that there is the need to relocate. And this time around, people saw the dangers, you know, that is going on, and some are now saying they are ready to relocate. The issue has been discussed, but I think government has to also ensure that areas are prepared to receive people if they should agree to relocate. So it's an option that is on the table. But again, you can't force people to move. You need to appeal to them to move. So the appeal is being done. Those who understand are moving, but I think we will get there where most people will fully understand and move away, because we can't afford to lose life because of flooding and sea level rise. Thank you.
Can I add a comment to that? That excellent statement already. So if we look at a new paper that came out, and I'm posting the link now in the chat. So this looked at the socioeconomic development and what is actually, let's say, happening according to what is in this paper, but also we see it also in other parts of the world, is that a lot of the economic, socioeconomic development and the growth is taking place in the vulnerable coastal zone. So rather than already, let's say, being smart with current plannings, a lot of the new activities are actually planned in this very, let's say, low-lying areas for short-term benefits close to the water, easy transport, etc., etc. So there's also this trajectory of development of simply developing, so to say, in the wrong area if you would take this long-term perspective. So that could be a big win if that is internalized in a lot of these activities.
Maybe also to answer the question on how much are local authorities and people already aware about the complex interactions between land subsidence, sea level rise, and drivers. I think that from the scoping study and the results we got at both the regional scales and also for Ghana and Nigeria, is that especially land subsidence is really a topic understudied in the region. So we know from the new INSAR measurements, we got that there are some subsidence, but as Pietro said, we also have quite some uncertainties because there are different data sets not showing the same rates. And erosion is a well-known problem and well-studied, and I think Professor ADDO will confirm. But really, to tackle all the three topics at the same time, subsidence, sea level rise, erosion, and their respective drivers is really an ongoing, I don't know how to say that in English, but it's an issue that definitely needs a further research.
Yes, can I come in briefly?
Yeah, sure.
Yeah, so Marie-Noëlle, you are right. Subsidence is not known in several agencies in Ghana. Erosion is well known now. Sea level rise is also well known, and it's well known because of the issue, the discussions around climate change, and again the challenges that we are facing with regards to flooding. Relating flooding to sea level rise and then climate change. But subsidence is not part of the topics that are being treated. And that is why I find the Engulf project very, very relevant. And then also the workshop that we are going to have in 2024, very significant, because the workshop is also going to be a medium or a platform through which awareness will be created within the sub-region for people to now begin associate some of these hazards within the coastal zone to subsidence, which is a topic that is not being treated in the sub-region. Thank you.
So we have about five minutes left. I don't know if there are any further questions or comments from the audience. I'm just looking at the chat if I missed any. There was one I forgot about, so from Mr. Vincent Roger, who asked, are there any projects in the region regarding contingency plans with both a technical and governance dimension, trying to effectively reach out to local communities? I think there are some. Maybe Professor ADDO can have comments on that.
Yes, there are projects that have plans reaching out to the local communities. I can talk about a project that I'm involved in. In fact, nowadays, most projects try to involve the local communities because we realize that they are the ultimate beneficiaries of these projects. So it is improper to undertake a project without involving, getting the buy-in of the local community. So projects we are doing now, we try to develop the project right from the onset with the local communities. So we do a project design with them, a project we are doing looking at nature-based solution to coastal erosion. We are involving the communities right from the onset, the design, the implementation of the project. So, and again, we also realize that the governance level or the governance at various levels are also very critical. So we involve the main stakeholders in terms of the governance structure in some of these projects so that there will be that buy-in and continuity so as to ensure sustainability. So I must say that yes, projects are ongoing that are involving local communities and also giving back to the local community the results that are coming up and ensuring that they own it. And once they own it, they're able to ensure the sustainability of this project. Thank you.
So there's also a comment on the Regional Observatory of the West African Coast as part of the WACA program. I think Professor ADDO, you're aware of this, and maybe you can comment on this. What I can say is that, of course, it's a kind of relevant institution, and we do plan to, and we hope and we do plan that the results of our research program will feed this observatory, and also to raise the subject of relative sea level rise.
Yes, the regional observatory it's ongoing, and what beyond the regional observatory, where we look at what is going on along the coastal area, we also come up with what we call the master plan, and the master plan tries to look at the issues that are ongoing within the coastal area, so as to come up with or to help with managing these challenges within the coastal area. And this regional observatory involves all the countries in West Africa, from Mauritania all the way to Benin. And we have scientists, and we have people from government who are part of this working group. And then these working group come together to, discuss what is going on there and document the issues that are related to coastal management in that region. So yes, the master plan is ongoing, and it's being patronized, and is effective, and is influencing decisions in the sub-region.
I see that there were some remarks in the chat about the fact that many people would like to have this conference also in French. So I'm sorry, I'm actually the only French speaker among us four. So and we don't have any automatic translation or translator available in this research conversation, in this kind of events. But for the future results of the Engulf program, and especially for policy brief and policy outreach documents, we will make sure that they are available in both English and French, so that the results can be also easily understandable in French-speaking countries of the region. I'm really sorry for those who are not at ease with English for this conference. Maybe we're arriving at the end of the webinar. I take the one last question about the use of optical images in addition to GNSS and INSAR data for scientific assessment. Maybe Pietro or Philip, I don't know.
Yeah, let's say optical data, let's say in the specific context of trying to understanding elevation and change of elevations, these optical data are not really useful. I can say they are not really used. And so at least for these specific goals, we do not take advantage of them. For sure, they are very useful for other investigation, erosion, or extension of flooded areas. But let's say these are not, at least within Engulf project, we will not take advantage of those kind of images.
So we're arriving at the end. I would like to thank again very much our three speakers, so Professor ADDO, Pietro, and Philip, for your very interesting presentation. So thank you very much for the discussion part. Thank you to all the audience for attending. And please keep, so new results are going to be released next year, available on AFD website or through webinar series. So please, I don't know how to say that, but keep on record. Can I say that? for new information. And I wish you all a very good afternoon, and I hope to see you again for future events within the Engulf projects. Thank you very much. And good afternoon.
Thank you, everyone.
Thank you, everyone. Bye-bye.